Alright, so this PowerPoint will be covering the findings of Lab 5. So just as a quick introduction, the purpose of this lab is to observe the forces on a falling magnet through what is essentially an aluminum tube. Using our knowledge of magnetic forces and induced current, we try to explain why our magnet seems to slow down, as well as what would happen if we change the setup for the experiment. Here's a list of concepts and corresponding formulas that will be used for this lab, including Newton's second law, magnetic flux with respect to time, EMF from a changing magnetic field, and magnetic flux, as well as the force on a segment of wire. Now, as to why we're using an aluminum tube for this experiment, if we were to use a ferrous metal such as iron or cobalt, our magnet would attract to the sides of the tube rather than fall straight through. Here's just a list of the measurements taken from this lab, including the dimensions of our aluminum roll, as well as the magnetic dipole moment from the last lab. For simplicity, I will be breaking down the code of the computational model into the steps of the lab manual in the order they are presented. So the first thing we want to do is set up our initial conditions. This is the screenshot up top and shows us coding in our aluminum tube. Down below you can see the function we'll be using to find the magnetic field vector at the locations of the rings. This function actually is pulled straight from the code of Lab 3. Next we want to define a function to find the rate of change of the magnetic flux, since we will be using these values to calculate the induced current, which you can actually see at the bottom. Now, using the formula that was shown on an earlier slide, we can actually find the force that the magnet exhibits on an individual loop. And if we sum up the forces from all of the loops and take the magnitude, by Newton's third law, we now know the direction and magnitude of the magnetic force on the magnet. Since we now know the magnetic force acting on the magnet, as well as the gravitational force, we can actually just add them together to find the net force acting on the magnet. And using the net force, we can calculate the change in velocity for the time interval, and then use that updated velocity to adjust the position for each iteration of the code. And this is what my model ended up looking like. On the right you can see a velocity graph for the bar magnet. Now, as far as interpretations from the computational model, since we know that the north side of the magnet is pointing down as it falls, dB dt will be in the negative y direction. As a result, the magnetic field from the wire will oppose the changing magnetic field from the magnet and point in the positive y direction, indicating that current is flowing counterclockwise in the right segments of the tube. The opposite is true for the south end of the bar magnet, which will induce a current in the clockwise direction, and if the magnet were to be flipped, it would actually take the same amount of time to fall through the tube, but the clockwise and counterclockwise currents would flip direction. Based off of the graph, it appears that the magnet initially speeds up in the negative y direction as it approaches the tube, slows down and stabilizes its speed once it's inside the tube, and then speeds up once again once it nears the end of the tube. This allows us to make assumptions on the forces acting on the magnet throughout its movement. Above the tube, the only force acting on the magnet is the gravitational force. As it approaches and enters the tube, it begins to slow down as there is now a magnetic force opposing the gravitational force, and once in the tube, the velocity is constant, signifying that the magnetic and gravitational forces are equal and opposite. And finally, upon nearing the end of the tube, the magnetic force begins to decrease as the magnet accelerates in the direction of the gravitational force. Now, if the magnet were to fall in free space as opposed to through the tube, it would actually fall faster since there would be no magnetic force opposing the gravitational force. If we compare our fall time in the real world to our simulated fall time, you can see that I was off by more than 200%. Although this drastic difference could be due to the quality of the materials used to perform this experiment, it is likely a result of me mishandling the magnet. Unfortunately, between the end of Lab 3 and the execution of Lab 5, my magnet suffered a rather substantial drop. As a result, the dipole moment is likely not as strong as it was for Lab 3, where we calculated the value used in this lab. To address some what-ifs, what if the resistance of the tube material was as close to zero as possible? Since resistance is inversely proportional to current, this would result in a larger current in the segments of tube as the magnet falls. In turn, this will yield a stronger magnetic field produced by the tube and therefore a stronger magnetic force on the magnet. As a result, the magnet itself would fall much slower through the tube. And what if holes or slots were cut into the tube? Well, if holes or slots or anything were drilled into the tube, it will make it much more difficult for the induced current to flow. As a result, this will reduce the magnetic force on the magnet and allow it to fall much faster through the tube.